Okay, welcome to the last set ever for this semester. It's a short one, we only have 2 exercises. I'll finish them. Then if you have any questions for the exam, let me know. So, starting with exercise 1. For each of the following algorithms, we want 3 things. Recursive definition of a function, pseudocode for the algorithm, and then prove the correctness with induction. And we've seen all these 3 parts before. So, for the first algorithm, write an algorithm, recursive obviously, to find the floor of a non-negative real number x. So you're given non-negative real number x, make a function that gives you the floor. Okay, fair enough. Let's see how they did that. So with the recursive definition, first of all, if x is less than 1, then it's just 0, right? It's non-negative, so it's, let's say it's greater than or equal to 0. And if it's strictly less than 1, well, the floor of this is just going to be 0. So that's kind of like your base case. Otherwise, you remove 1 from x, and you add 1 to the answer. So this algorithm is saying, hey, you have, let's say, 3.7. Is 3.7 less than 1? No. So the floor of this is going to be the floor of 3.7 minus 1, which is 2.7, then plus 1. Now, same as before, is 2.7 less than 1? Not yet. So it's going to be 1.7 plus 1 plus 1. So like you keep adding 1s to your answer until you finally reach your base case, which is, hey, this is now less than 1. So the floor of this is going to be 0. You have 3 1s. So the answer is 3, and that's correct. Great. What about pseudocode for this? Well, literally, you just have to translate what you have with your recursive function into code. So you get x, which is a non-negative real. If it's less than 1, return 0, like we did here. When you finally reach your base case, it's less than 1, you return 0. Otherwise, recursively call the function, remove 1 from x, and add 1 to the final answer. So floor of 3.7, it's going to be 1 plus floor of 2.7. So like we said before, this function doesn't have an answer yet because it's waiting on this function. And same as before, this is going to be waiting on 1.7, 1 plus 0.7. We reached the base case. We know the answer for this is 0. Now you backtrack all the way up. So the answer for 1.7 is going to be 1. Because 1.7 is going to be 1 plus this, which is 0. The answer for 2.7 is 1 plus 1, so 2. The answer for 3.7 is 1 plus 2, so 3. So you keep going all the way down till you reach your base case. When you're done, you're no longer recursively function. You backtrack all the way up. Prove by mathematical induction that this is correct. Okay. So base step, if x is less than 1, the floor of x is going to be 0. And that happens right here. Hey, x is less than 1, it's going to return 0. Done. Inductive step. We're going to assume that the floor of k, like the function floor of k that we wrote, the algorithm, is actually going to give you the floor of k, where k is non-negative real. Now we want to prove it for k plus 1. Remember this floor of k, like this is just a function name. It happens to be the same as this. But you could have called this my function. Floor of k is going to give you this. It's going to give you this. Now we want to prove that the floor of k plus 1 is going to give you the correct answer. So what's floor of k plus 1? Is it this? We can't. Okay, so is it this? We can break down floor of k plus 1, the actual floor, into k alone and plus 1 alone. But we did prove before that this is our assumption. So you're done. Okay, any problems so far? Okay, makes sense. Like it's the floor of the number before it plus 1. So like if we were doing it for 4.7, it's just 3.7 plus 1 using the recursive function. But we know that this equals the floor of k plus 1, and you can add the k here, like if you're doing it in reverse, and that's how you're. In the statement, they just wrote it in reverse. The second algorithm from here. Two non-negative integers, x and y. We want a recursive algorithm such that they get multiplied together, but they want it in O of log n. And they gave you a hint on how to do that. Well, if you were just multiplying x and y, you could have just said, hey, it's x times x times x, y times. But the problem with this, if it's gonna be O of y, and y could tend to infinity, could be n, whatever. So this is like O of n, O of y. But no, they want an O of log n. So they gave you a hint on how to do it. Why does it work? You don't really have to care. It's just given. So x times y is going to equal this. If y is even, it's going to equal this if y is odd. Okay. So recursive function. You have three choices. If y is 0, sort of like this is your base case. Because remember, every time, if you notice here, every time y is getting divided by 2. So like y is decreasing, eventually it's going to reach 0. If y is 0, the multiplication between x and y is going to be 0. If it's even, we just wrote what they told us. If it's odd, same thing. So that's the recursive definition. Now the pseudocode. Y is 0, return 0. Y is even. How can we test for this if y is even? You can just say y equals 0. If that's the case, return 2 times the recursive call depending on what parameters you need. So x is going to be the same, but y gets divided by 2. Return, multiply, xy. Okay, so now for the odd, this is one way of getting the floor. Y minus 1 divided by 2, or you could use the previous function we wrote upstairs. Okay, so for the even part, you just have to divide by 2. But for the odd, you want the floor of the division by 2. So you could just remove 1 from y. That should work. Okay. Deal. And you have the plus x, of course. That's just what they told us. Why does this work now? Base case, y is 0, the multiplication is 0. Easy stuff. In the inductive step, so in the previous algorithm, we did it for using mathematical induction or simple induction. Here we're going to need strong induction. Why? Because every step we're dividing y by 2. We're not subtracting 1 from y. If you do this, it's like, okay, assume k is true and prove for k plus 1. y gets you back here if you're only removing one, like we were doing in algorithm 1, sort of, yeah. But when you divide y by 2, you go way back. So that's why you need strong induction. Just assume up to k is true. And we did just that. Assume that multiply xj is going to give you xj for any j between 1 and k. That's strong assumption. Now we want to prove it for k plus 1. Cases. If k is odd, k plus 1 is going to be even. So our algorithm says it's going to equal this thing. This part is just plugging in what they told us. Multiply of x k plus 1 is going to be this, since k plus 1 is even. But what's this? This falls within the realm of your assumption. K plus 1 over 2 is going to be in this range, in your assumption range. So you can substitute it with the actual multiplication of x with y. Expand, you get x into k plus 1, which is what you want, right? When you multiply x by k plus 1, you want this. Multiplying x by k plus 1. We're just proving that our pseudocode works. Okay. If you didn't get that, maybe try now with the even case, because it's the same thing. We start with k. It's even. Okay. We know that now k plus 1 is odd. So multiply x by k plus 1 is going to equal this, depending on our, actually all the way down here. Because of our pseudocode. But same thing, k plus 1 minus 1 over 2 is going to be way less than k. So you're in your hypothesis, you can just now substitute it. You can just multiply x by this other parameter, which is just k over 2, when you remove 1 and 1. Expand, you get xk plus x. Take x common, aha, that's what I really want. Like, yes, it worked. Multiply x into k plus 1 is going to give you x times k plus 1 in both cases, in all the cases. Okay, algorithm 3. Given a non-negative integer n, we want a recursive algorithm to find this thing, a power 2 power n. It should be in O of n. In order to do that, they gave you a hint. So at any point, a2n plus 1 equals a2n, all of it squared. So this sort of tells you your recursive algorithm is going to have 2 calls. What do I mean by 2 calls? Well, for the second algorithm, we had this. If k is even, you do something. You do one call, which is calling the recursive function multiply once. If it's odd, you do a different call. Again, multiply depending on whatever plus x. In both cases, you're only doing one recursive call. It just depends on k. But here, there's going to be a case where you're multiplying a power 2 power n. And when you're doing this, so a power 2 power n plus 1 equals this. This is doing 2 recursive calls. We'll see it to better understand it. Starting with the recursive definition. It equals a if n is 0, right? A power 2 power n. If n is 0, that's a power 2 power 0, just a. That's your base case. Otherwise, if it's bigger than 0, we did what I just said, right? So a power 2 power n, it's like a power 2 times removing 1, 2, then you can just square the whole thing. And minus 1, all of it squared. Or, yeah, okay, so that's enough. That's enough for what they wrote here. It's just the n before it squared. Now down to the pseudocode. Same thing. N is 0, return a, otherwise return the multiplication. But this being squared, it's like you're calling it twice. This is equivalent to saying return power n minus 1 a times power n minus 1 a. This is what I meant by you're calling the function twice. So this isn't really efficient because you're calling it twice. Something better would be to store it in a variable. So like make some variable temporary equals power n minus 1 a, and then multiply temp by temp. This would be better because of reducing the number of recursive calls. Okay, let's prove that this is true. If n is 0, done. For the inductive step, assume for any non-negative integer k. So this sort of hints to strong induction. But I wonder if we need it. Okay, now we want to prove it for k plus 1. This is the hint they gave us. And you're done. Take a minute at that, and we'll see if we'll repeat it. Okay, so again, like it would have probably been easier to understand if they wrote it like this: power a k plus 1, according to this thing, n is not 0, or like k plus 1 is not 0. So it equals power a k squared. And we already know what this is, right? It's just a power 2 power k because it's less than or equal to k, and all of that gets squared. So you get a 2k plus 1, and that's how you're done. I'm noticing they may have flipped the integers. Maybe here the integers are flipped. Yeah, here it should be power a and then n minus 1. But that's okay. It's just a spelling mistake, right? Like the function you said, it takes first the integer a and then it takes n. So when you call it, you should give it the values in the right positions. Okay. Exercise 2. If there's anything not clear so far, let me know. For the following algorithms, we want the recurrence relation and we want the big O notation. So we did a similar exercise, the recitation. So what's the recurrence relation? Like the current function with its recursive calls. And then whatever that is, what is the complexity of it? So first one, It's a linear search. What does linear search mean? You have a list, you keep going through it one by one till you reach the element that you want. So this usually linear search is going to be O of n. Why? The worst case scenario, the element you're looking for is at the end of your list. So you have to go n times till you find it. So what's the relation? Base case, t of 0 is 1. Like if you only have one element in your list, or you reach the end element, it's only one step, which is, or actually I think by 0 they might mean that you have no elements in your list, so you just return -1. Like you don't have any elements, or it might depends on what 0 means and how many elements they take. So if 0 means the number of elements, hey, you just return -1. You don't have any elements. Or if it means you only have one element, hey, just return a of 0. Nevertheless, what's the recurrence relation? This thing. Why? What's happening? T of n. Let's say both of these first ifs are wrong. They cost you, right? You checked, is index less than 0? No, so that's 1. Is key equal to this? No, so that's another 1. 2 plus the recursive call. And you're recursing on the same list of elements, but the index is decreased by 1. So like the actual number of elements you're gonna be now checking is index -1. So tn -1. Instead of 2, you could have just wrote an O of 1. Even if this was 20, 200, as long as it's something that's constant, you can say O of 1. Now the relation. Well, if Tn is related to its previous by removing 1 and adding 2 here, then same thing. Tn -1 becomes this plus 2. -3 plus 2, so on till you get 2n. And we know that 2n is similar to n over 2, to n over 4, to 4n. It's just t of n. By here, I'm not saying, hey, we keep dividing. I'm just saying O of n over 2 is the same as O of n, O of 2n. That's why I said here, even if it's like 20, it's just going to be at the end O of 20n. And up to a certain constant, these are all the same. Okay. Second algorithm, ternary search. So without diving too much detail into this, it's sort of similar to binary search, but where in binary search we look at the middle of the list, like you break down it into 2 halves. Here we're breaking it down into 3 halves. And then depending on our if statements, we see which half we want to continue with. So with the binary search, oh, can you please? Okay, so you had a problem with algorithm 1? Okay, so first, okay, fair. So first of all, do you understand this code or not? Okay, in case you don't, you have your list. It's from A1 up to AN. Depending on how they wrote it, you start this code at n. Like when you call this function, you give it A1 and n. Then they check, is index negative? That just means that you went through the entire list and you didn't find the element that you want, because every time this is going to be decreased by 1. Then they say, is the element you're looking for So does the element key equals A of index? Actually, let me see if I can find some white space. Okay. So we're just going to explain the algorithm. A1 up to AN. You start the function with n. This is just the index, and we want to see if we can find this element here. So it starts like this. If you find it, let's say you don't find it, then you decrease it by n minus 1. And you keep decreasing it until it's the first element. And if even after that you don't find it, that's when you return -1. So the purpose of the first condition, if index is negative, this just meant that you kept looking at your list and you weren't able to find the element. So just return -1, like the element which is key, it's not there. Otherwise, if it is there, like if key equals A of index, in other words, it equals this element I'm currently at. And the index is this thing here. It starts at n, so you're like checking the last element. If it's not that, then you check before the last, all the way till you reach the first element. Okay. If that's the case, then if you do find the element, great, just return index. Like you're done. You're saying at which position the element you were looking for is at. Finally, like if you haven't reached the end of the list, and if this current element is not what you're looking for, then all you're left with is return the recursive call, which is your function name. You give it the same list, and you decrease index by 1. So is that more clear? Give an example with numbers. So let's say I have 1, 2, 3. This is my list. Okay, and I have my key. Let me see how they took the parameters. Okay, so you have your list, you have your key, and you have right and oh, sorry, that was the second algorithm. Same thing, you have your list, key, and index. So let's say I have 1, 2, 3. My key is 4, and I start index 3. So the first 1, 2, 3, that's just your list. A1, A2, A3. Second is the value you're looking for, which is 4. And this is the starting index. So I check, does A3 equal key? Like, does the value 3, it happens to be the same thing. Does the value 3 equals 4? No. But before that, you check is if 3 is negative. Also no. Then just return 1, 2, 3. You're still looking for 4. The list is the same, and you're still looking for 4, but now the index got decreased by 1. Is the index negative? Not yet. Does A2 equal 4, which is your key? No. So again, 1, 2, 3, the list is the same. The key 4 is the same, but the index got decreased by 1, and at the end, you're going to return -1 because 4 is not in your list. Okay? So that's it. It's just linear search, but in reverse. Okay, so you didn't, now you're saying, how did we get to n minus t? This is plus t of 0. It's just 2 plus 2 plus 2 plus 2. You have it n times. Okay, so you started with tn. It equals tn minus 1 plus 2. Then it equals tn minus 2 plus another 2. You keep decreasing n by 1 till you reach t of 0. And for every one of those t's, you got 2, 2, 2, 2, 2. So it's just like 2 plus 2 plus 2 n times plus 1. So 2n plus 1. But all of that is just O of n. Okay? Let's continue. Unless you still have a problem here, let's try to understand the second algorithm. T of 0, it's just this, 1. Like the base case, if we assume that 0 is the number of elements, if you have no elements, you just return -1. Like you're calling the function, no elements, you're looking for the value 100, and since you have no elements, then index, you start at 0 or whatever. You have no elements. So you just return -1. Like the value you're looking for, there's no way you're going to find it because you don't have any elements in your list to search for. So T of 0 is just 1. But the relation T of n with its recursion, it's +2. Because you have this, it's 1, and then this is 1. That checking, this statement, is index less than 1? This costs you 1. Then this thing, does it equal? No, that costs you another 1. That's why we say 2 plus the recursion. Okay. Good. If it's not 100% clear, that's fine. Let's just see another example, another exercise. Maybe that'll help us out. So back to this one. Ternary search, like I was saying, it's similar to binary search. So with binary search, if we have, actually, did they assume that the list is sorted? They should, right? Okay, so they're not stating it, but I assume that this list is going to be ordered, sorted. So with binary search, you have your elements sorted, you check the middle one. Like let's say 1, I have here 55 up to 1200, and I'm looking for 99. If in the middle I have 55, then that means I should be looking in this area, right? This is sorted, so 1, 5, 55, maybe here 100 till I reach 1200. I'm looking for 99, and I checked the middle element. It's 55, so that definitely means if I'm gonna find 99, it's gonna be in the right-hand side. So now I keep checking this thing, and I check in the middle again, and so on. With ternary search, it's you break it down into 3 parts, and you do something similar to see which third you want to check in. So for example, you check this thing. So again, let's say 55, 100, 1200. If I check the first third and I see it's 55, well, that means 99 is going to be somewhere here. And I check the second third, I get 100. Now that means 99. If it's going to exist, it's going to be in this middle third. So now when you recurse, you check only the middle part. It's kind of like you got rid of these 2/3. Okay. So again, similar to whereas in binary search we only break it down into 2 halves. Here we break it into 3/3, and we see in which third we should check. So this gets you the indexes, right? You check. If you find it, you just return the element. Like if 99 is here or here, just return the index. You're done. Otherwise, if it's less than the first third, so if it's less than 55, I return this part. I check this part. If it's bigger than the second third, I check this part. If I reach the last else statement, it just means it's not smaller than this and not bigger than this, so it has to be in the middle. So I return that. Actually, the return part only happens here. What you do here is you're just fixing the parameters. Okay, your left and right. Again, in binary search, you only need sort of like the middle. Here you're going to need two operators, left and right. Okay, even if we didn't get it, even if we didn't get how algorithm works, we can still do a relation with it, right? So what's happening? How many statements am I doing? 5. Okay, so again, base case is 0, like you have no elements. That's just 1. Return -1, let's say. Otherwise, what do you do? Okay, so 1, 2, 3, 4, 5, and so on. Like it might be a little more than 5, but like they're kind of saying that you have 5 steps. First, you're checking if it's in the first third, then in the second third. Then if this is true, you'll change right to this. Otherwise, you'll change left to this, and so on. So like you have 5 steps. It might be slightly more than exactly 5 statements. But the recursive call is definitely going to be n over 3. Yes, breaking down the list into 3 parts, exactly. And why is the recursive call only n over 3? Because like we said, we broke it down into 3 parts, depending on our if statements, no matter how they magically worked, but depending on that, we choose one part to continue with. So at every recursive call, your list is cut down in third. Okay? In binary search, every time it's cut down in half. Here it's cut down in third. So before we check what happens with the relation, we know that binary search is log base 2 of n, right? Because if n is the number of elements, every time you divide n by 2, it might be, and we're dividing by 3, as you see, n over 6, n over 12. What should the answer be at the end? Log. Because every time you're dividing, that just means log. Whatever the value you divide on, that's the base of your log. So in binary search, we keep dividing by 2, 2, 2. So it's going to be log base 2 of n. Here we keep dividing by 3, 3, 3. So it's going to be log base 3 of n. O of log n, yeah, exactly. It's O of log n. It's going to be, but what's the base? It depends on on the value that you're dividing by. Okay. So again, if we assume that n is a multiple of 3, you get this is going to be k. If you just substitute it, actually no substitution yet. So yeah, we're saying how many 5s do I have here? It's log base 3n. Like how many times do I have to do each of these 5s? Well, you keep dividing n by 3, 3, 3, so it's log base 3n times. Okay, that's your final answer. So it belongs to base log 3. Again, these 5s, you could have just imagined they're O of 1s because they're constants. At the end, we're saying how many times am I doing this constant? It's log base 3 of n. Similar to the binary search idea. Do you have any problem with how we got the log base? Okay, good. Okay, deal. Okay, so if this question, so this is like ternary search, it's just dividing it by 3 parts. You could make your own, don't know what we'll call it, where you break it down into 4 parts, and then depending on these values, you'd see which part you take. You might take this part. So this, every time you're dividing by 4, you'll get its log based 4 of n. Now, so if you break it down into 4 parts, and every time you're only taking a quarter instead of a third, it should be faster, right? It's only log base 4 of n. Now, one thing actually to take into consideration, this is ternary search, and this is, I don't know, quarter search or whatever. But we know that we've heard of binary search way more than ternary search, right? Like, why is this more famous, or maybe even more used than ternary search or quad search or whatever? Well, it's true that binary search is log base 2 of n, and ternary is log base 3 of n, and the bigger the base, the faster the algorithm should be. But in practice, it might not be that. Like, how many times do we call log base 2? How many times are we gonna call log base 3? That's gonna be a difference in the speed. So if you have the time, try to do your own research and just say, hey, binary versus ternary search. Why is binary used more? Okay, it's not just that the code is clearer. I think it's like in the worst case scenario, because there are scenarios where ternary search is better, where binary search is better. But I think in the worst case scenario, binary will perform better. Okay. I don't think this is required in your exam, this much details, but it's a nice thought to keep in mind. On to the last algorithm and the last part in this assignment. Same idea, but now we're doing power. So x power n, we want that. Okay. And this is similar to what I was saying maybe in exercise 1, where we're doing 2 recursions. Okay, this is doing 2 recursions. So before we actually dive into the solution, just like if we want to throw in some ideas, T of n in this case, the relation is going to be 2 times T of n over 2. Like, you're calling it twice. You're not calling it once, okay? So if you were calling it only once, like in binary search, right? In binary search, what's the relation? Every time divide by 2, maybe plus something. Then it equals n over 4 plus something. That something is O of 1, something constant. So every time it keeps getting divided by blah, 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 by 2, that's why it's O of log n. But here it might not be as clear, okay? Because you're dividing it by 2, but you're doing it twice. So that might slow it down. This is why we have Master's theorem. I think this might work in Master's theorem, where we can get an answer for that, like the complexity. You could have used, by the way, Master's theorem to, if it works with the rules, to get this, to get the complexity. Anywho, so base case, T of 0 and T of 1. So what's T of 0? The number x, its power is 0, so you just return 1. It's one step. You check that n is 0. If that's the case, you return 1. Otherwise, if it's 1, so x power 1 is going to be x. It's the second if statement. You check if n is 1. Why is it 2? Because first you checked if it's 0. That was not the case. Then you checked it's 1. That was the case, so you get 2 checks. Then we reach the recursion. If it's if it's even or not. If it's even, you do this. If it's odd, you do this. This is just constant times x, but what we care about is that in both cases, you're doing the call twice, the recursive call twice. Okay, so it's 2 times n over 2. 3 because now we've done 3 if statements. Is n 0? Is n 1? Is n even? So that's the 3 plus 2 times n over 2. Now let's see what they say. We start off like this. Now what's the relation with n over 2 with n over 4? Same thing, just recursive. So n over 2 is going to be 2 times n over 4 plus 3. We expand, we get this. Same as before, it's going to be 2 into n over 8. We expand, we get this. So you can see it's n over 8, but you're doing it 8 times. 9 and 21, let's say that's O of 1. Maybe it's more. But what I care about is this. For n over 2, you're doing it, okay, this is actually grammatical. It should be over 4. So n over 4, you're doing it 4 times. N over 8, you're doing it 8 times. So it's not really log because you're doing it a lot of times. So if we assume you keep doing it until 2 power k, so log n equals k, substitute the values. Okay, you can focus on this on your own time. It's just plugging in some algebra. 2 power log anything, maybe that's something. So 2 power log n is n. Ta-da-da. You get this at the end. Okay. Again, you can read this on your own. What I care about is you reach that t of n is 4n minus 3, which is O of n. Okay, so it seemed like it should be log because every time we're dividing by 2, but you're doing it a lot of times, okay? Okay, so let's see just one last time what's exactly happening. You start off with power n over 2, let's say. I know there's an x, but I want to focus on n over 2 because x stays the same. So what's the answer for, actually, let's start with n. What's the answer of this? It's going to be power n over 2 times power n over 2. Like it's recursively calling this twice. Whoops. Okay. Then this same thing, n over 4, n over 4. And this is the same thing, n over 4, n over 4. Like, okay, so n over 2, you're going to do it once here and once here. So that's twice. But now n over 4, you're going to be doing it 4 times. And n over 8, you can see it's going to be done 8 times. So it's right that you keep dividing by 2, but you're doing it a lot of times as well. Like if you divided it, if we reach the eighth division, you're dividing by 8, but you're doing it 8 times. So it's not like you didn't really benefit, okay? And why is it really annoying? Because it's the same thing, right? Power n over 2 here, it should give you the same answer as power n over 2 here. It should be the same answer. So why are you doing it twice? I think if you'd had created a temporary variable, like we said in exercise 1, and said and put the answer in it, so power x n over 2, and then multiplied that temporary by itself, I think this algorithm would have been log n. Why? Because, okay, so you start here, you go down this road, you put it in temp, and then you multiply temp twice. But it recursively calls here, so you create another temp, you put the answer in it, and you multiply it twice, and you keep going, okay? I'm gonna Need some white space because it's not very clear. Because it's allocated in memory, we don't have to calculate it every time, 100%. Exactly. Okay, so power n over 2, n over 2, n over 4, n over 4, n over 8, and so on. So before you'd have to do this, and then multiply it. But like you said, Reem, instead, since they're the same value, calculate it once, put it in a variable, and multiply that variable by itself. So now I don't have to recurse on the right-hand side and do all of this again, because it's enough for me to do this. And again, say enough for me to do this. So you can see, instead of branching out and calculating everything in this tree, I'm only going down one line. And what's happening in that line? I'm doing n over 2 once, I'm doing n over 4 once, n over 8 twice, n over 16, sorry, I'm doing n over 2 once, n over 4 once, n over 8 once, n over 16 once. I'm only doing it once for each of those, so it's going to be O of log n. Like in this big tree where it keeps expanding a lot of times, you're only taking one branch, one line, one root. Okay? So you can see it just simply creating a variable and putting the value in it would have been so much better, because remember, O of log n is tremendously faster, quicker than O of n. And by faster, here I mean it takes less time to finish. I don't mean it grows faster, because obviously n grows faster than O of log n. Oh, okay. So that's that. I think all the problems are over. If you have any questions on this assignment, or any assignment, or any recitation, or any question, let me know now. Otherwise, good luck on your final exam. Okay, and assignment 6. Let me go get that. Do you remember what your question was? Like in which problem it was in? Okay, it's right here. No need for this. Okay, so remind me, which question was it? That's fine. Oh, is it the flooring? The pseudocode could be troubling many times. What do you suggest we do so that we're keen on the flow of steps? What do you mean by the flow of steps? Is it this one, Majd, what you were talking about? Okay, how did you prove the omega? Sure. So for this, how did we prove the omega? Okay, so first step, we only said this, it's greater than or equal to this. Why? Well, what's the floor? Oh, sorry, what's the ceiling of x over 2? Could be two things. If x is divisible by 2, it's just going to be x over 2. If x is not divisible by 2, like if it's odd, then it's going to be x plus 1 over 2, right? Like if x is, let's say, 4, so 4 over 2, it's just going to be 2, so that's done. Otherwise, if x is 3, what's the ceiling of this? It should be 2, so it's like you're adding 1, 3 plus 1 over 2, you're done 2. Okay, so the ceiling is always going to go up. So the ceiling, it's going to be either x over 2 or x plus 1 over 2. Well, if you compare both of these with x over 4, it's going to be bigger than them. Okay, x over 2 is definitely bigger than x over 4, and x plus 1 over 2 is definitely bigger than x over 4. Do you agree on that? Okay, so that's how we got this and this. As for the second part, what about the ceiling, the floor of x over 2? Again, it's going to be bigger than x over 2 minus 1. Because the ceiling of x over 2, it could be divisible by 2 or not. If it's divisible by 2, it's just going to be x over 2. If it's not divisible by 2, it's going to be what? X minus 1 over 2. Both of these are smaller than x over 2 minus 1. Then this part, let me just check this. Yeah, exactly, because x over 2 is definitely, both of them are, sorry, bigger. So x over 2 is definitely going to be bigger than x over 2 minus 1. And the other one is just going to be x over 2 minus half. So it's obviously going to be bigger than x over 2 minus 1. So in both cases, with the ceiling, it's bigger than x over 4. With the floor, it's bigger than this. And eventually, we get this multiplication. This isn't the only way to do it, but what we care about is eventually we reached greater than something x squared. Okay? The reason we put this is because, well, first of all, we want the bigger than, right? This bigger than sign. With both of these, you had to replace it with something that was smaller than it, respectively. And when you multiply x by x, you're going to get x squared. So the x squared part is easy. All you have to do is just replace each of them with something that is bigger than them. Bigger than them and related to x, right? You obviously weren't going to say it's bigger than 1 because then, okay, it's bigger than O of 1. Great. We want it to be bigger than O of x squared. Okay? So it had to be in general. Let me know if that made it better. So, Reem, you're saying sometimes you can miss out steps thinking that they're already implied in another when we have to explicitly state them instead. Okay, great, Majd. What do you mean, like, you can miss out steps? Well, like the whole point of the algorithm is to break down your idea into as many small steps as you can, especially when we are used to specific coding language. Okay, like, so you're saying when you're, like, if you're using Python and you then want to use pseudocode, okay, instead of pseudo, I think I understand you. Like if you're using Python and then you have, let's say, a function that does the sorting for you. You mean this? If you use the sorting function, it's okay. I see. Hmm. Like this, the algorithms that are required of you are going to be very simple. So if you are using Python, just think of yourself if you're using anything that's a shortcut is what I could say. Like, what are we going to be using? For loops, while loops, and if statements. That's it. There's really no need for shortcut. If you think it's easier to just use algorithms in that case, then sure. But I don't see the like if you did you try to solve these problems like these that we just saw? Like for example, this algorithm. If you're doing it in Python, there's really no shortcut, right? You're checking is this 0, is this 1, modulo, then return power, the recursive call. Like there's no shortcut that I can see you doing if you translate it into Python. I think if you just try to solve a few problems, for example, in the palindromes last week, okay, remind me what happened. You said something, right, that had to do with a for loop or something. Okay, I remember what you said. What you did last week was you wrote one statement that reversed. Okay, so in last week we had a palindrome. What you did, you used one statement to reverse a string. So for example, if we had madr, you wrote in one statement something that changes this into the reverse. And then you checked if both of these are equal. Yeah, this is obviously a shortcut when you use one statement to like reverse a string. You had a loop in a loop. I don't remember that. I remember this thing where you change an entire statement, a string into its reverse using one word and then checking if both of them are equal. Whereas if you were doing it in pseudocode, what would you have to do is make 2 pointers at the start and the end and keep checking. Or you could do this reverse thing, but you'd have to do it on your own. Like make a new string that's empty, start a pointer at the end, and keep adding it character by character here. If you did this, that's fine. I'd have to loop the whole word from both sides or assign a temporary value. Exactly, that's it. That's it. You just have to do that. In the exam, you can definitely ask if you're allowed to do a certain function or not. But you can see it like this is an obvious example where no, I'd have to break it down into more steps. Okay. Okay. So I hope that answered you. Anything else? Yeah, definitely. Like we're not saying don't solve it in a certain way. Solve it however you want, as long as you show all the steps. If you wanted to reverse the string and then compare them, that's okay. You just have to show the steps of the reversal, not just write a magic function that reverses it on its own. Okay. As long as we don't say how to solve the problem, like unless we tell you, hey, do it in using step 1, 2, and 3, you can do it in however A, B, C you'd like. Yes, I think Dr. Bilal said it's fine to use Python in the exam as long as it wasn't specified you use something else. And again, just show all the steps. Okay, great. You're very welcome. Okay, so you can, again, I think if you have any questions, let me know. Otherwise, the forum, and I think you know the story by now. Very welcome. I'm glad it was helpful. Okay, good luck on your exam. Yeah. See you next time.